Alright, so guys, in this video we'll be treating finite groups. So when we say finite group, a finite group is simply um a group that have the underlying set to be finite. So whenever you have a set that the underlying set is finite, it is a finite group. So we have the set of integers. We have z5 and it is enclosed in a group of addition. Now meanwhile, if it is an addition, the group here can be addition, it can be multiplication, it can be division, it can be subtraction, it can occupy any of the mathematical variables. So we are asked to check if z5 is a group. Of course, if it is a finite group. So if it is a group, definitely is a finite group. So this is a finite group. Another example of a finite group is z6 z6 plus. This is also a finite group. This is a finite group. Z7 multiplication. This is also a finite group. So all of these are finite groups. So we have to check if this is a finite group. So we start with we have 0 to 4. So we list all the elements. Now if it is z5, we list from 0, 1, 2, 3, and 4. And similarly for the horizontal part, for the vertical part, you list from 0 to 4. Now we start adding. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. Then we move to the second part. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. Now 1 plus 4 is 5. So what we do is that we do 5 divided by 5. 5 divided by 5 is 1, remainder 0. So it is the remainder that we are going to write here. So you write down the remainder at this region. Now you divide it with the 5 that is given here. Right? Similarly, 2 plus 0 is 2, 2 plus 1, 3, 2 plus 2, 4, 2 plus 3, 5. Now, anytime you have 5 above, 5 and 5 above, what you do is that you divide it with whatever you have here, the integer which you are proving with, and you write down the remainder. So 2 plus 3 is 5, 5 divided by 5 is 1, remainder 0. So it is the remainder that we are going to put down here. Now the other one, 2 plus 4 is 6, 2 plus 4 is 6, so 6 divided by 5, 6 divided by 5 is 1, remainder 1. So you see we put 1, remainder 1 here. So similarly, you do the same thing for every other thing. So we have our table completed. So we have to check if it is a group. Now this is a group and it is a finite group. Reason because we have an identity element. Our identity element is 0. Now because we have plus here, we have a multiplicative identity, an additive identity. We have two major type of identity. We have the additive identity. Additive identity is 0, while multiplicative identity is 1. So our identity is 0 here. So we also have an inverse. We have an inverse. Check if you notice that 1 times 1 here, or let's say yes, 1 times 1 is 2. 1 times 1 is 2. This 1 multiplied by this 1 is 2. Now let's check 1 times 2. 1 times 2 is 3. Similarly, 2 times 1, 2 is also 3. 1 times 2 is 3. Similarly, 2 times 1 is also 3. So it simply means that we have an inverse element. So these are the angioms. These are some of the angioms that shows that a particular identity, a particular set is a group. Right now, another proof that we need to check is the commutativity proof. Now it is commutative, right? 2 times 1, 1 times 1 is 1, 1 times 1 is 1, 2 times 1 is 3, 1 times 1 times 2 times 1, 2 times, check, if you check, sorry, it is not times, 2 plus 1, I mean 2 plus 1 is 3. Now let's check for the other one. Let's check 1 times 3. 1 times 3, look, 1 times 3 is 4 in this case. So for this region, it is not commutative. It is not commutative. Let's check if it is commutative for the other one. 3 plus 0, 3 plus 0 is 3. 3 plus 0 is 3. Now let's check if another one, 3 plus 0 here is also 3. So it is commutative for this region. So you just need to prove all of the axioms in a group to show that something is a group. So most importantly, this is a finite group because the underlying set is finite. So the underlying set is finite. Assuming you have z infinity, this is not, I mean z infinity, this is not a finite group. Z infinity and plus, this is not a finite group. So that is that for this video.